Hi, so some students had some questions with Chapter 3, Pre-Calculus by Larson, Section 3. So I'm going to go over some information with you guys. First, a little lecture on what this section is about. First of all, we're going to use what's called the CBF, change of base formula, and show you how to do that, and show you the formula about that. Okay. The second thing we're going to be doing is learning about the expansion of logs and the quotient, power properties, and all that stuff, and then use it as well. So what is CBF? A change of base formula. It says that log base A of B, that's base A, we can actually write it as a quotient, which is the log of B, that's the top one, that's the big guy, over the log of A, and we could use any base we want. In this case, we could use base 10. We learned a little bit earlier, which is called common log, or we can use natural log as well. Natural log of B over the natural log of A. So here's an example on page, example 1, on page 207. It says, what is the log base 4 of 25 equal to? Right? So you can actually use your calculator as well if you want. Nowadays, the TI-84 actually comes with log bases now. All you have to do is go to Math right over here, press Alpha A, that will give you the log. Log base 4 is 25. Well, let's actually try to figure out what this is by hand. To change this into exponential state from the previous lecture for Chapter 3, Section 2, is base 4 to what power is equal to 25? Well, that power, if it's 4 squared, 16, 4 cubed is 64. So that question mark is going to be between 2 and 3. 4 to the second power is 16. 4 to the third power is 64. So it's going to be actually closer to 2. I would probably venture to say it's probably going to be 2.2 to 2.3. So let's actually see. Log, I have never tried this before, so I might get a really bad answer. Log base 4 of, and I used the right arrow key to get to the number, log base 4 of 25. And 2.3. Whoop, there it is right there. If you can see it, is 2.3. So I'm pretty close to 2.2 and 2.3. Actually, it's a little bit above 2.3. So that's approximately 2.322 approximately. Well, we can change this into, I'm going to use a different color pen. Let's use red. If I use common log, I use common log of the top, which is 25, over the common log of 4. Okay, and let's try to do this on our calculator. You go log right there, that's the common log of 25, and parentheses divided by the common log of 4. I usually don't need the end parentheses on this one, 2.32. So you notice that these are the same exact answers, and we got it right, because I checked it. Check. So you should be able to do natural log as well. It's going to be the natural log of 25 over the natural log of 4. You can check it with the calculator, okay? And that's that. I'm going to put a little thing right here. Now we're going to do the next section, which is not example 2, but before we start going over the product property, which is on page 208, we're going to be doing what's called the exponential state, and then the radical state. So if I have a to the b over c, so you notice that it's an exponential state because we have an exponent right here. To change this into what's called a radical state, this becomes what's called your index. So here's a symbol. This is your index right over here, which happens to be C. And the B is on the top or the outside. There's your base to the B. We can write it this way, or we can write as the index of C, A, and then we can put the B, which is that portion, the numerator, on the outside. So you could put on the inside or the outside. It depends. It doesn't really matter. Okay? But we know that if we're in a radical state, we have a radical symbol. So this is called the index. The inside information is called a radicand. And this is a radical symbol. That was a pun. Radical symbol. Okay, got it? Isn't that radical? So we have to understand, are we in the exponential state? We have to get back to what's called the radical state. Or if we're in the radical state, we have to get into the exponential state. So what are some of the rules of the product property for logs? Well, the log of u times v, I don't care what the base is equal to the log of u plus the log of v. So the log of the product becomes the sum of its logs. So let's try another one. The log of u divided by v, what do you think that is? If you want to pause and think about it. If the product is a sum, then the quotient must be log of u minus the log of v. Like I said, I don't care what base you use. You can use any base you want. Okay, base x, base x, base x, base x, x, x. It doesn't really matter. You could use natural log, which is the most common natural number, or you can use base 10, which is the common log. Now, another thing that you should know is the log of a to the b power. This is the beauty of logs. The beauty of logs is that the exponent can actually come down to the front, or you can come back to the top. So it's b times the log of a. So the number that's being multiplied in the front can go to the exponent, or if it's at the exponent, you can come down. That's the beauty of logs. Okay, just to let you know. So let's do example 3 now. I'm going to change this a little bit. I can't see it very well. Here it is. This is page 2. Example 3 on page, what is that? Page 208. So part A is natural log of 6 is equal to what? It says write each logarithms in terms of natural log of 2 and natural log of 3. Well, obviously natural log of 6 is 2 times 3 is 6. We expand it out, that becomes natural log of 2 plus natural log of 3. And there it is. A product becomes a sum, so natural log of 2 plus the natural log of 3. Let's try part B. Natural log of 2 divided by 27. That's the same thing as natural log of 2 divided by 3 cubed. Notice that right there? 27 is 3 cubed. So that's a little tricky right there. That becomes natural log of 2 minus natural log of 3 cubed. Notice that the numerator is right here. Minus is a quotient. Natural log of 3 cubed. And the beauty of log, remember what the beauty of log said? This comes out to the front. So rewriting it, that becomes natural log of 2 minus 3 natural log of 3. If I evaluate this on my calculator, and I evaluate this in my calculator, I will get exactly the same answer. Okay? And that's that. Do I want to do example number 4? I don't want to do example number 4. Let's do example number 5 now. Example 5 gets a little bit more, what is the word? Complicated. Example 5a. Log base 4 of 5x cubed y. So what this is saying is we're going to expand the log. It's 5 times x cubed times y. So when we expand it out from a single log to a multi-log, this log base 4 of 5 plus, because it's being multiplied here, log base 4 of x cubed plus log base 4 of y. And the only thing we have to do is the beauty of logs, which is that 3 comes out to the front right there. And so the answer is log base 4 of 5 plus 3 log base 4 of x plus log base 4 of y. There's your answer right there, okay? That's answer 5A. How about 5B now? 5B gets a little bit tricky. Natural log of square root of 3x minus 5 over 7. Now you notice that we have a little bit of a problem here because of this radical. You have to change a radical state into a logarithmic, a exponential state. So the first thing is we're going to change this radical state to an exponential state. This portion right there is 3x minus 5 to, because this is a 1 right there, and what is the index here? If there's nothing there, the index is 2. It's a square root. So the 2, the denominator, is the index, and 1 is the exponent. Make sure you can go from radical state to an exponential state. So expanding this out, you get, that becomes the natural log of 3x minus 5 to the 1/2 minus, because it's a division, natural log of 7. And the beauty of logs is that you bring this out to the front. There it is. And there's your new answer. Okay. I'm not going to do this problem for you. Finish up. You should be able to finish it up by yourself. If there's only one more example, so I'm going to go over that lastly. Okay. Let's do example 7 now. Example 6. This is page 3. Example 6. There's 3 parts to it. It says part A, 1/2 common log of x is base 10 plus 3 times common log of x minus x plus 1. Well, the first thing before we start condensing into a single log, you have to get these exponents. The coefficients or the numbers back up to the exponent right over here. So when we bring it back up, here's what it's going to look like. Common log of x to the 1/2 plus common log of x plus 1 to the 3rd power. Is that fair? You got that? What's the x to the 1/2 power? That's the same thing as the square root of x. So when we do is we put it into a single log, you get common log of square root of x times x plus 1 to the 3rd power. And you change it from a multi-log into a single log. Okay. Example B, 2 natural log of x plus 2 minus natural log of x. Well, the first thing we do before we change it to a single log is we like to get rid of that 2. The beauty of logs is bring it to the exponent right there. So what we end up with happening is natural log of x plus 2 squared minus natural log of x. And to condense into a single log because of this minus, we put this guy in the numerator. Natural log of x plus 2, this whole thing squared over x. A little tricky on this guy. It's not the natural log of x plus 2 squared over natural log of x. It's just one single thing on the inside. There's no natural log in the numerator nor the denominator. Let's do part C now. 1/3 times log base 2 of x plus log base 2 of x minus 4, and try to figure out from a multi-log into a single log. Well, what we can do, you don't like to put the 1/3 all the way up to the front first because PEMDAS says we should work from the inside first, right? So that becomes log base 2. Since we're adding here, we multiply these two things. It's going to be x times x minus 4. Is that right? X minus 4, right. And that's going to be multiplied by 1/3. So the 1/3 now goes to the exponent of this guy right over here. That on the outside right there. So that becomes log base 2 of x times x minus 4. And this whole thing to the 1/3 power. If you want to change this to a radical state, since the 3, the denominator is the index, that becomes log base 2 of cube root. Notice that the index becomes the denominator of x times x minus 4. I don't know what the book says. Yes, that's what the book says. You can distribute this out if you want, or just keep it as factored. Good luck on your homework, guys.